The ideal gas law, section 11.7. This is the last section that we're going to cover in chapter 11 for the gases. There's a couple other sections that we're not going to cover. You're more than welcome to look over them. The book has a lot of nice pictures and other realistic applications. Some of them I discussed in other video lectures, but the book supplements that. So the last one that we're going to cover is the ideal gas law. Now, the ideal gas law focuses on a current set of conditions for a gas. All the other gas laws that we looked at, you had this initial and final comparison. Initial set of conditions change to a final set of conditions. Or here are the final conditions. What's one of the initial conditions, okay? So this looks at a current set of conditions for a gas. Now, the word ideal means you think, okay, it's something that you're aspiring to go to, the ideal situation. In reality, real gases actually follow this equation. In most cases, the only cases where real gases would not follow this mathematical equation here is if you have conditions of extremely high pressure or extremely low temperature. And then you have something called the van der Waals correction factors come in, but that's not for Chem 110, okay? So the ideal gas law, current set of conditions for a gas. Now this gas law, we have to watch the units. Previously, the only thing we were really particular with was the temperature. We said any gas law that you do any calculation with, you must have temperature in Kelvin. That still holds true for the ideal gas law. But now we have to make sure that we have the pressure in atmospheres. We have to have the volume in liters. We need to have the moles of the gas. If we have grams, we're going to have to convert grams to moles using molar mass as a conversion factor. Okay? You say, why? Why do we need to have these units of atmospheres, liters, moles, Kelvin? Okay? Well, we now have this constant that is part of this relationship here. PV, pressure times volume, equals the amount of moles times the ideal gas constant times temperature. R is the ideal gas constant. It's used in every single ideal gas law calculation. You will have this number in every problem that you're using this formula for. What is the ideal gas constant? 0.0821 with units of liters times atmospheres over moles times Kelvin. See this here? This is why these need to be like that. They need to match, okay? Liters, liters, atmosphere, atmosphere, moles, moles, Kelvin, Kelvin. Okay, so the ideal gas law, we need to be particular with the units. Okay, so if we have anything different than these units, we need to convert them. Let's do some problems with the ideal gas law. Okay, you have the one online lab number 8. It's actually, coming up. Okay, it's actually in the same week that this is going to be posted. Okay, so experiment 8. You'll see that you have pressure readings in millimeters of mercury. You'll need to convert to atmospheres. You'll see that you have volume readings given to you in milliliters. You'll have to convert to liters. And you'll see that you have temperatures that need to be converted to Kelvin. All right, let's do some problems here. Okay. In a lab experiment, 47.45 milliliters of hydrogen gas was produced. Okay. So if we were doing the reaction with the magnesium metal and the hydrochloric acid in lab, hydrogen gas is produced as a result of that. It's a single replacement reaction. You have the hydrogen gas that is produced and the magnesium chloride aqueous solution as well. So the hydrogen gas is produced as a result of some reaction, and it's measured that a certain quantity, certain volume is produced. So let's say this is the volume. Okay, so in a lab experiment, 47.45 milliliters of hydrogen gas was produced at 24 degrees Celsius and 754 millimeters of mercury. How many moles of hydrogen gas were produced? Okay, this is a calculation you're going to have to do for experiment 8. Okay, you're going to have to calculate the moles of the hydrogen gas produced. All right, so we have a current set of conditions. Hydrogen gas, okay, we have its volume, we have its temperature, and we have its pressure. We need to use the ideal gas law, but the ideal gas law is particular with units. So first we want to check the units. Do we have the temperature in Kelvin? No, we need to convert. Do we have the volume in liters? No, we don't. We need to do that. And do we have the pressure in atmospheres? No, we need to do that. So check units. Temperature, we need to convert 24 degrees Celsius to the equivalent Kelvin. So we would add the 273 to the 24, and we get the 297 Kelvin. Okay. Volume. Volume in milliliters, convert to liters. Okay. So we check this unit, and we check that. So 47.45 milliliters, convert it into liters. 1 liter has 1,000 milliliters. Okay, so that would give us 0.04745 liters equivalent. All right. And now we need to convert the millimeters of mercury into atmospheres. So pressure in millimeters of mercury, convert to atmospheres. Okay. So we have 754 millimeters of mercury, and in 1 atmosphere we have 760 millimeters of mercury. Cancel out millimeters of mercury, so now we have 754 divided by 760 to give us 0.992 atmosphere. Okay. All right. Now we need to use these numbers to plug into the ideal gas law. Okay. So let's hold that there. Okay. Because I need to erase this board. Let me just write my numbers down so I don't forget. Okay. Because I have to erase the board. Okay. All right. So first we check the units. Second, we need to set up the ideal gas law equation. Okay. Pressure. We have the pressure. 0.992 atmosphere. We have the volume. Moles we don't have. That's what we want to solve for. Okay. Now you like the other gas laws, you can rearrange the variables if you want first. Okay. I don't show it that way because we're learning this, so it helps you to recognize pressure, atmospheres, volume, liters. Okay, but if you want to rearrange the variables first, if you look at that and you say, I need N, and you would rather rearrange the variables first, you can, depending on your comfort level. But I'm going to show you without doing it that way, so you can see, I have this, I don't have this, and then rearrange your equation from there. R is the ideal gas constant. You're going to use it in every calculation where you use the ideal gas law. Okay, so I'm writing the ideal gas constant. And then your temperature is 297 Kelvin. Man, I'm really pressed for space. All right, 297 Kelvin. Okay. I should have shifted that a little bit more. All right, we want to solve for N. So we need to divide both sides of the equation by the ideal gas constant and by the temperature. Okay, so I'm going to do that here. Because you see, this is your unknown. So what you do to one side of the equation, you need to do the exact same to the other side. Okay, so these will cancel out. Okay? Let's look at the left-hand side of the equation. And let's look at what units cancel out. Atmospheres cancels out. And atmospheres cancels out of the ideal gas constants derived units. Liters. Kelvins. And what does that leave us with? Units of moles, which is what we're asked to find. How many moles of hydrogen gas? Okay. Now, when you put this into your calculator, you're taking this product and dividing it by this product. Use the brackets. If you put this in without the blue brackets, I cannot guarantee you're going to get the right answer. But if you put in where I have the blue brackets, if you use your parentheses here, okay, no, right here, sorry, I pointed at the wrong thing, then you will get the correct answer. Okay, now, okay, open parenthesis. 0.992 times 0.04745, close parenthesis. Okay. Division sign. Let me just scroll that back so you can see that from the beginning. Okay, sorry for the glare. Let me try to block that glare. Okay. I've just entered in my numerator. Then I did division. Now I need to do an open parenthesis and put the product for the denominator. So 0.0821 times 297. Close that final parenthesis. You should have two sets of parentheses. Equals or enter. Okay, then you get this number. All right, and we're going to round that to 3 significant figures. So it's a small number. All right. .00193 moles of hydrogen gas. Okay, we're going to drop those other digits because they're not significant figures. Okay, it's very important to put these parentheses in. Otherwise, I can't guarantee that your calculator is going to give you the right answer, right? Because what your calculator may do if you do not put those parentheses in, if you omit the parentheses that I have in blue, or the brackets, I'm sorry, and you do 0.992 times 0.04745, and then do division sign, 0.0821 times 297. If you omit the blue brackets, okay, which here you'd enter the blue brackets in with the parentheses, what your calculator may do is multiply this and then divide only by the constant, not by the constant times the temperature, okay? So just be careful with that. And we'll do another example with the ideal gas law, okay? Okay. An oxygen tank contains 131 grams of gas at 1.10 atmosphere. At 28 degrees Celsius. What is the volume of the oxygen gas? So we have an oxygen tank. Okay, somebody may need an oxygen tank to supplement for their breathing, okay? All right, maybe you have maybe there's a larger tank and then it's put into smaller tanks. So let's just say that there's an oxygen tank containing 131 grams of oxygen gas at 1.10 atmosphere and 28 degrees Celsius. And when you want to know what the volume is of this. Okay. It's no final and no initial and final conditions. You don't see any unit repeated in here. So that's your clue that it is the ideal gas law. Plus you see grams, okay? The other problem, we had the term moles in there, okay? Whereas the simple gas laws and the combined gas law don't account for moles. We assume that the moles are constant and they're not part of the calculation, okay? So we have 131 grams of oxygen gas at this pressure and at this temperature. All right, we need to check the units. Check units. Okay. Do we have pressure in atmospheres? Yes, we do. Okay, 1.10 atm. So we don't have to convert the pressure. If we would have had torr or millimeters of mercury, we would have had to convert, but we don't. We have it in the unit that we need it in. Temperature in Kelvin. We need to convert Celsius to Kelvin. Okay, so 28 degrees Celsius plus 273 gives us 301 Kelvin. Okay, let me just make that a little neater. Okay, so now we have our pressure in the units that we need it in, and we have our temperature in the units that we need it in. Okay. All right, we have grams of gas, and we need to have the moles of the gas. All right. We need to convert grams to mole. Now, we learned molar mass in Chapter 7, and it never goes away. We have to use molar mass a lot. For instance, now, when we do the solution chapter, and if you take chemistry, the next course up, 121, even 118, molar mass you need to use as a conversion factor. So we have 131 grams of oxygen gas. Then we want it in moles. Okay? So oxygen has an atomic mass of 16. We have 2 because it's diatomic, so 32 grams per 1 mole. That's the molar mass. 32 grams of oxygen per 1 mole of oxygen. We want the grams to cancel out. So again, we're using dimensional analysis because anytime you do conversion, it's the best way to do it with dimensional analysis. So the resultant moles of oxygen gas, 4.09 moles of oxygen gas. Okay, now we have everything to find the volume. Okay. So we have this information here that we're going to now plug into the ideal gas law. Okay, pressure. Do we have the pressure? Yes, 1.10 atm. Do we have the volume? No, that's what we're asked to find. Do we have the moles? 4.09 moles. Do we have the ideal gas constant? You bet. You're going to use it every time that you do an ideal gas law problem. And temperature, we have the Kelvin equivalent 301. Okay. Pressure, pressure. Volume, volume. That's our unknown. Moles, moles. Ideal gas constant, ideal gas constant. Temperature, temperature. Now we need to get the volume by itself. So solving the problem using algebra, divide both sides by the pressure of 1.10 atmosphere. Cancel, cancel. You look at the right-hand side, cancel out units that are similar. Atmosphere, atmosphere. Mole, mole, Kelvin, Kelvin. We are left with units of liters. Now we have to do the math. Okay, so 4.09 times the ideal gas constant times the temperature. That product divided by 1.1 gives you a volume of 91.9 liters. Okay? And that's like a steel cylinder, a pretty big steel cylinder. So probably would be shipped from a warehouse and then put into smaller containers for personal use. That's a pretty big volume there. Okay, 91.9 liters. Okay. Okay, so this concludes the chapter 11 topics with the gases and terminology and gas laws. After viewing these, if you have any questions, make sure to contact me. If you want to go over anything in particular or show you another example individually, let me know. But with the videos, you can pause and go back as well. There's that feature with that. But if anybody has any questions, please let me know. And please keep up with the problems in the textbook to help you with the material. Okay.